All right. So let's go very fast to review some of the basic things we discussed with Gaussian mixtures, and then we will try to generalize into some applications. So I'm going to go rapidly just so I can give you sort of a brief overview of what the terminology. So we started with the multivariate Gaussian, and I gave you the formulas for the mean and the covariance representing the MLE solution, okay? So look at this carefully because we will be getting similar forms, but weighted with some posterior probabilities. All right, so we discussed the fundamental problem in mixtures, and here what you see is three Gaussians basically separated. So this is P of x given the color of the Gaussians. So this is the red, the green, the blue, all right? This is the marginal. This is the Gaussian mixture, the same thing in 3D. And these are points basically drawn from the distribution P of x, okay? And in principle, if you want to draw the samples, what you need to draw is first the index k with probability pk, and then for each k that you select, you generate an x from this Gaussian n of x given mu k and sigma k. All right, so this would be the ideal problem, right? If we have data and the data come with labels, with colors, then we can deal with it. But the real problem is basically when the data are coming uncolored, okay? I mean, here there is the same color, but when I mean uncolored, we cannot separate what Gaussian generated the data. All right, so this is the task. Basically, somehow, can we extract the information that you see on the left? Can we extract that information from the picture on the right? So we started by introducing a latent variable for each point x. We call that latent variable z. All right, so z is the coloring that tells me from what Gaussian each point x comes. And we wrote the joint distribution of x and z, all right, as p of z, p of x given z. And also in some sense, you know, I gave you this in the implementation. If you're gonna implement this, the z matrix basically will have one row for each data point. And if we have three colors, the variable z will be taking values 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, let me just keep going. So we wrote basically the conditional distribution of x given z like that. All right, this is sort of you know, a sharp way of writing things, and we have used this before. So if we knew if zk is 0 or 1, right? Obviously, it's going to be 1 for one of these components. For the rest, it's going to be 0. So then it will give us the appropriate Gaussian that generates x. We also wrote the prior like this, all right? So the joint distribution looks like this. And we didn't really do it explicitly because it's not very difficult to see it. If you take this distribution and you integrate z out, so you integrate for all possible values of z, then you actually get the Gaussian mixture, okay? Literally, if you have not done this, or if this looks cryptic to you, just take this expression and start summing it for z that is 1, 0, 0, then z 1, 0, 0, 0, 0, 1, and then you will see immediately that you get the Gaussian mixture. So the question is, of course, what have you gained by introducing z and writing things like that versus writing, you know, p of x directly as such? And we will see this in a coming slide, the complexity. But before I see on the slide here, we have the definition of the responsibilities, right? And the responsibility is basically a posterior probability that for a given x, it tells us that what is the probability that we have a color being blue or being green or being red, okay? So we call this posterior responsibility gamma, and there is one basically, for each x there is one gamma, okay? But remember, the assignments that are being done with this posterior responsibility, they're not hard assignments. You don't say this is 100% blue, 100% red. So a point may be a little bit blue, a little bit red, and a little bit green, and you see this, all right? So when you assign colors in proportion to the responsibilities, you don't get this plot that contains the exact true identity of the points. You get something like that. So away, for example, from the central region, these points, yes, they are all red, these are all blue, but somewhere in between they have colors that contain a little bit of red, a little bit of blue, and a little bit of whatever else we had on those plots. All right, so the complexity comes from this picture. If you work directly with the likelihood, effectively what you will have is you will have log of the sum of Gaussians. All right, that is no good. All right, and no good because this looks simple here, but you can appreciate working with a log of the sum of Gaussians. It doesn't take advantage of the fact that this is a nice exponential, right? If you had the log operating directly on the exponential, then the exponential will disappear, and that would be very nice. But now, because you have this summation, that is not going to happen. In the notes, by the way, there is a lot of graphical representations of the model. And for those who have not taken probabilistic graphical models, that most probably I will offer in the fall, I don't want to throw things that we have not seen in this course, but sort of you can appreciate the type of dependencies that this diagram implies, right? So you can see xn, which is given because it's my data point, so I mark it with a dark color here, depends on Zn. You can see Zn depends on pi because that's my prior model, and xn, all right, given Zn, depends on the mean and the covariance sigma. So this diagram sort of shows you the dependencies that you have in the problem, and in principle, if you have this diagram, it's equivalent to all the equations you have seen up to now. In other words, you don't need to write any equations because this diagram itself implies everything you have seen up to now. We talked about the pathologies of MLE for Gaussian mixtures, and if you try to implement this in the homework, for example, you will come sooner or later in this pathology. So one of them is the likelihood becoming infinity, and we explained that possibility is when the center of one of the Gaussians coincides with one of the data points xn. So in that case, when sigma goes to 0, this Gaussian goes to infinity. And if you try to maximize the likelihood and you use a sophisticated optimizer, it will basically, if it is smart optimizer, it will take it to infinity, right? Because there's nothing wrong with that. You want to maximize the likelihood, this is what's going to happen. So in your case, if you get a situation like that, what you need to do is you have to have sort of some condition there. If this happens, just escape from this, okay? So if you escape, hopefully you will not come back to it. There is an issue with identifying the labels, because when you say this is the mean and the variance of component 1, the mean of the variance of component 2, is 1 the blue, or it's 1 the red, or it's 1 the green, right? So there is a serious identifiability problem, and because we have k factorial equivalent solutions, and in principle, and we will do this today, hopefully, if you do, Bayesian modeling, even if you do just a map estimation, a lot of these issues, not all, but a lot of these issues will disappear. All right. So let me bypass this. So we came to the AM algorithm, which is extremely fundamental everywhere in machine learning. All right, not just in the context of Gaussian mixtures. As a matter of fact, I'm going to try to apply today the EM algorithm in the context of regression and things we have seen, so you can get an appreciation of how powerful the algorithm is. So the EM algorithm iterates basically between two steps. On the first step, it computes the responsibilities for each data point n, And in the second step, basically optimizes the parameters, the mixing coefficients, and the mean, the covariance of the Gaussian. The subject is so important that literally there are books just written on the EM algorithm, right? I know the second book decorates my bookcase and has lots of very interesting aspects of the EM. The E step is calculating of the responsibilities that look like this, right? In some sense, what you see here is Bayes' rule, all right? So this is the conditional distribution given J, and this is the prior of J, divided by a normalizing factor. And notice why we need iterations, because to compute the responsibilities, you need to know the parameters, the mean and the covariance, right? If you don't know them, you cannot compute the responsibilities. So there is no closed form solution. And if you take the likelihood and you maximize it with respect to the parameters, you get results that look like the MLE estimates for a multivariate Gaussian. So the mean, you remember in the multivariate Gaussian is the sample mean, but here looks like the sample mean, but the points are weighted by the responsibilities. And if you think carefully, right, it's sort of like taking each of the Gaussians separately and saying, I'm going to do an MLE for each Gaussian. But you have to account for the points that belong to each Gaussian, and the points that belong in each Gaussian are defined by gamma in a soft manner. Right? So if you look at each Gaussian, you say, what's the mean? Is the sample mean. So here, you're not going to take all the points equally, because some points don't belong, all right? Or some points belong in part, everything defined by these posteriors. So you weight them by gamma. And Nj, of course, is the, if you like, the number of effective points that belong on the Gaussian J. Okay? Similarly for sigma j, again, looks like the sample covariance, and pi j is basically the empirical count, if you like, that you see in these models. Takes all the points and see what's the fraction of points defined by gamma that belong to the Gaussian J. All right. I don't want to give you any proofs because the proofs are trivial, and I'm just going to click rapidly the results. So basically, if you have this data that they're with the same color, you decide to do this with two Gaussians, let's say, and a blue and a red. So the first step is the E step, to color the points. So those close to the blue Gaussian will become more blue, the rest more red. All right, and I remind you, more blue and more red, they actually have both colors defined by gamma. All right, so once you decide the coloring, then you have to recalculate the mean and the covariance of the Gaussians, and this is here. And then with those fixed, you recolor the points, and you keep going and going, and in a few iterations, you converge. Obviously, you know, the likelihood may have no unique maximum, right? So you may find some local maximum that you settle, you know, and unfortunately, that's what you get with this type of problems. And again, this is the same type, another implementation. All right. And you can see actually, if you take the log likelihood, it actually converges very nicely in very few iterations. So in this faithful, basically, data from Bishop's example, I mean, I can see here in practically 2 iterations, the likelihood has more or less been maximized. All right. The only thing I'm going to say about initializing this EM algorithm, basically the standard way to do it is using k-means algorithm. Okay? So somewhere in your start of your program, you should have some initialization based on k-means. And there are multiple ways to actually, multiple versions of this EM algorithm for Gaussian mixtures. Even in the starting point, I see here it says, so when you start the algorithm with k-means, very, you know, this would be a U, of course, right? There's no such an English word. So this is an algorithm that is very typical on to initialize with k-means, is called the furthest point clustering without reading. So let me just get out of this page. Can you tell me what, if you're going to initialize, what would be sort of a trivial way to initialize, let's say, 3 clusters? Thinking of this algorithm called the furthest point clustering. So let me start the algorithm. You pick up one of the points to be the center of one Gaussians. All right? What should you pick up as the second center of the next Gaussian? Just to initialize, and thinking that this method is called the furthest point.
The one that's farthest away.
The one that is furthest. So basically you select the points with probability that is proportional to the distance of each point from the centers, from the clusters that you already selected. Okay? And obviously if you already selected 2, then again you will find the one that has the maximum, so you calculate the minimum distance from the centers of the clusters you selected, and then from those you pick up the point that has the maximum distance. Now there are algorithms actually, and if you search, even you will see MATLAB implementations where you start with a number of clusters, and then somehow they keep scores for each Gaussian, and if the scores are high, they split those Gaussians into Gaussians. And if the scores are very low, they take 2 nearby Gaussians and they merge them. All right? But the most principal way to do this is literally to start with a mixture of infinite Gaussians and let the ones that are not important to disappear. And the way to do this is to use a Dirichlet process as a prior. We will do this with the Dirichlet distribution, but if you use a Dirichlet process, you can actually use an infinite mixture of Gaussians. All right? So let's talk, nothing sophisticated yet, but let's talk about an abstract presentation of what we have done up to now. So we started basically with the likelihood, this is the log likelihood, and we wrote it in terms of the joint log likelihood, all right? This distribution of x and z, right, is the joint log likelihood. This is if you knew the colors, right? This is the joint log likelihood, but you notice here, obviously, to get p of x, you have to integrate z out. So the only information that we can compute about z is through this posterior that you see there. Okay? All right. So we said it would be ideal if somehow we knew this joint log likelihood, right? And it would be ideal because if this is in the exponential family, so if this is a Gaussian, when you take the log, you will get the exponent of the Gaussian, all right? So that would be ideal, but we don't know z. So we cannot really work with the log likelihood, the joint log likelihood. So the next best thing to do is work with what? Work with this quantity that you see here, which is the expected joint log likelihood, or complete data log likelihood. And the expectation is, with respect to the posterior of z, compute it at, because we're going to be doing EM iterations, right? Compute it at the previous set of parameters theta. So in the E step, effectively, what you need to do is you need to compute an approximation of the posterior, all right? These are the responsibilities, but we compute them with the previous set of parameters, right? Remember, we fix the parameters, we compute the responsibilities, then we will see, with those responsibilities, we do the maximization problem and update the parameters, and we keep repeating. So if you, you fix the parameters, right? You compute the responsibilities, which are these posteriors, and then as a post-processing step, since you already have computed an approximation to the posterior, you compute the expectation of the complete data log likelihood. All right? Look very carefully at that equation, right? So we said the joint log likelihood, this complete data, the word complete data means x and z known. right? We don't know Z, but if we knew X and Z, right, I can write this log likelihood, the joint data log likelihood. And because we don't know Z, instead of working with the joint log likelihood, what do? We take the expectation of this with respect to the approximate posterior computed base step. Right? So this is the expected complete data log likelihood. Okay? Expected, you can see the expectation, complete data X and Z, log likelihood. Okay? And that's the A step. And then what we do in the M step, we basically compute the parameters theta that maximize this expected complete data log likelihood. And then we keep iterating until theta and the responsibilities here converge. Okay? Now we will see on the forthcoming slides that actually, okay, this looks like an MLE, right? Working with this expected complete data log likelihood, but if you put some prior on theta, you can modify this and actually you should be able to compute with almost zero additional effort to compute the map estimate of the parameters as well. Oh, and here it is actually, all right? So if you put some prior on the parameters, basically you can just modify the M step where you find the parameters theta that maximize this expected complete data log likelihood plus the log of the prior. All right? So let me now go back and look at these equations, the general equations in the context of the Gaussian mixture, okay? So would you agree with me in the Gaussian mixture, the joint distribution of X and Z was looking like that? So if we knew Z, right? If we knew Z, would you agree with me that the joint data log likelihood would look like that? If you take, so you assume they have n data points, and you know both X and Z, right? That's the joint log likelihood there. So if you knew both X and Z, and you take logs, and you sum in n, you will get Z and K times the log of pi k and the log of the Gaussian. We agree? All right. Now, can you tell me, since I have, now when I write this equation, I don't know Z, all right? I said if I knew Z, this is what we have. And because we don't know Z, we said we're going to take the expectation of Z. So what's the expectation of Z for our problem, for the Gaussian mixture? What is it? Say it again? The expectation of Z. What's the expectation of Z? Remember the Z variable is binary, 1 and 0. What is for a binary variable, what is the expectation is equal to what? The probability. The probability, let's say that Z and K is equal to 1. And how do we call that posterior probability? What name we gave it?
Responsibility.
The responsibilities. So what you really need to do is write the joint data log likelihood like this, and then go and substitute Z and K with gamma and K. That's all. Because, right, the expectation of Z and K is the same as the posterior probability of Z and K being equal to 1, and that's the responsibility gamma and K. Make sense? Yes, no? Perhaps? Okay. All right. So the rest, basically, I'm just working to recalculate for you all the things we had before. And here is a proof, by the way, for a binary variable, right? That the expectation is the same thing as the posterior probabilities, which we call them gamma. Okay. All right. I don't need any of this. So the expectation, these brackets there, the way I have it, they indicate the expectation of the complete data log likelihood require nothing else but write the joint log likelihood and substitute Z and K with these responsibilities, which we call them gamma and K. All right, and there is nothing there of interest. And then basically, so In the E step, right, we calculate the responsibilities, and as a post-processing, if you like, we calculate the expected value of this joint log likelihood, and then you start taking derivatives with respect to pi k, with respect to mu k and sigma k, and then you get the familiar results that look exactly like this. Now, this concept of forming the expected value of the joint log likelihood is extremely powerful, and it's going way, way above Gaussian mixtures, all right? Every time there is latent variable, something you don't know, you always do some sort of EM type of optimization, and you literally compute some version of this expected log likelihood that you maximize, okay? So this is universal. It's not, I am going to show to you this in the context of regression, but the idea is not just for Gaussian mixtures. That's why I wanted to repeat these lectures and tell you about a little bit about the EM algorithm. I'm not going to do this slide, but let me just say the following, that if you have a Gaussian mixture, and you can actually, so you remember the Gaussian mixture and the EM algorithm, right, does assignments to each Gaussian component that they are not, how you call this, they are not one or, blue or nothing, red or nothing. They are soft assignments. But still, you can take the EM algorithm, and in some limit, you can actually derive precisely the k-means algorithm. And the way to do this is to assume literally that each Gaussian has the same covariance epsilon, all right, that we are going to take to go to 0. So each Gaussian looks like this, okay? And then when you compute the responsibilities, this again, the standard formula, the responsibilities in this case for this conditional Gaussians, they look like this. And if you think carefully, the only way for these things not to be 0 as epsilon goes to 0 is what? Look at this expression and see what is the only way for this thing to be finite, all right, so it doesn't blow up, as epsilon goes to 0. Don't read what it says on the bottom, right? Look at that thing. As epsilon goes to 0, each of the terms goes to infinity. So you get 0 over 0. So the other way to avoid that singularity is when? When this term in the numerator is equal to what? To the maximum term of the denominator. Right? Because the other term should be 0. And the maximum term in the denominator, when do you get it? When this quantity here that you see, xn minus mu j, becomes minimum. So effectively, when k becomes the argument j that minimizes the distance of xn from the centers, all right? Then this gamma z and k that you get, it actually becomes the same as the R and k we use in the k-means algorithm. If you forgot about it, right, so go back and review what the k-means algorithm was doing, and look at this equation as epsilon goes to 0. So the responsibilities basically in that case become the R and K we had in the k-means algorithm, and literally you can show by looking at the equation that the expected complete data log likelihood, maximizing that likelihood, is the same thing as minimizing this distortion measure that we used when we did the k-means algorithm. Okay? All right, this is just as a parenthesis. 12:59. Okay, so let me, I need to be selective on what topics we can do today. How many slides this is? Okay, maybe we can do this fast. So let's do a mixture that does not involve Gaussians. All right. So we're going to take that we have a vector of deep binary variables xi. I from 1 to d. And its variable xi is a Bernoulli distribution with probability mu I, okay? So these are independent given mu, these xi's are independent. So p of x given mu is mu to xi, 1 minus mu to 1 minus xi, all right? Where xi takes the value 1 or 0. So again, I have d variables, they're binary, and mu is the mean, okay? So if I write this as a vector now, all of them together, all right? So x and the mu like this, then the expectation of this is mu, and the covariance is basically the diagonal of mu 1 minus mu, okay? So you notice there is no correlations between those d random variables. This is very important, right? They are independent. That's what it is. So if you really want to have binary variables and you want to correlate them, right? And you can think infinite applications where that is the case. The only nice and easy way to do this is to actually take a mixture of those d binary variables. And so you construct similarly to Gaussian conditionals. You have these conditional distributions being distributions that look like the first equation. Okay? So, here is a mixture, all right? So what would be interesting is to see how do we do MLE estimate, how do we apply the EM algorithm for this type of mixture where the conditional distributions are Bernoulli distributions. All right. I am not going to do all the algebra, all right? But I'm going to give you two fundamental results. Look at these two equations here. They are relevant to our problems, all right? But I want you to look at these two red equations because this is what I use in the next two slides. If I have, so remember in my problem, I have, when I have the mix, right, I really have the conditional distribution of x given the label k. So what I write here is that the expectation of x is the expectation of x given k times the probability of k. You remember this from basic probability rule? And I can do the same thing. Instead of x, I can use actually x transpose and write the covariance of x, right, as the expectation of x transpose that I approximate like this, minus the expectation of x times expectation of x transpose. So when you plug in these things for the Gaussian mixture, what you get is something very interesting. You actually get a covariance matrix that is fully covered. Basically, these variables now become correlated, all right? And that's the main reason why you use this type of mixture model. And I will show you some examples in the following few slides, all right? But you can see immediately that somehow these variables become now correlated. So let's see one example. We have the MNIST data set, okay? We try to fix the number of components to 10, all right? So we basically have 10 centroids here. I mean, there is no, that's the means of these components are the only parameters that we need to compute, and of course, these mixing coefficients. So if you do an EM implementation of this problem, you get basically results that look like this. So on the top, what you see are the mixing coefficients, and on the bottom is basically the centers of the clusters of each of the mixtures, of the mixture components. So without reading anything, it contains a lot of information there. If you look at this, so these are centroids, right? These are different clusters that you get. So what is the immediate observations that you can see from this plot? Like I can see immediately on the first row that there is a problem there. So I gave you lots of handwritten digits, right? You put them in a vector form, right? And these are Bernoullis because they are black or white, right? So you use the mixture, and then you found me the centers, right? Of each of the components, which are letters, all right? That's what they came to look like. And what can you say about the centroids here? I mean, some of the things you can say. I mean, I'm assuming that this is 9 and not 4, right? You can immediately see that some centers, some letters are repeated. All right, so it doesn't know that they are different, and obviously it's because this model, if you write 9 or if you write 4 that looks like 9, it doesn't know the difference. All right, so it gives you something like that. And if you really want sort of to resolve these problems, you can actually play with this algorithm. You can see that you need to use way higher than 10 clusters to actually get anything that makes sense, okay? And of course, even then, because the likelihood is not convex on this problem, the solution that you get may not be a global optimum, so you may be trapped on something that is not what you are looking for. So let's see how the results look like, right? They are the same sort of as Gaussian mixtures. So this log likelihood looks like that is not a good thing to work with, because again, we have log of the sum of these Bernoulli distributions. So what we will do is we will introduce Z. So the conditional distribution of X will look exactly like for the Gaussian case. The only thing, this is going to be a Bernoulli, and the prior is exactly as before. And if you write the joint data log likelihood, will look like this. Look at this equation. Would you agree? Are you happy with it? Right? So remember, from there is an exponent there. It will come down when you take logs. And then what do I have? I have log of the mixing coefficients pi. And then where did this thing came from? Where did I get this? Because each point x is what? It's a vector of d dimensions, and each component of that vector is what type of distribution? Is what? Each component of the d vector is what distribution? It's Bernoulli. All right? So, so basically this is what I have, right? So these are my data points. These are the clusters that I have, all right? And all right, so basically there is a centroid that I have to compute for each of these d variables, all right? That's why there is an index I, and for each of the components k. All right, so if you want to do the EM algorithm, literally, you don't have to change anything from before. The only thing you need to pay attention is that Z and K now, when you take expectations with respect to the posterior of Z, is going to become the posterior gamma. All right? Exactly, that's what we had before with the Gaussian mixtures. So, the answers basically look the obvious ones. Let me see if there is a better slide with the results, all right? So let me, so let's define these two preliminary variables, all right, which again are common sense. What's the physics? Look at this nk. What is with words nk? Remember, gammas are posterior probabilities that the point n belongs on the cluster k. So what is nk? With words, what's nk? So the same as in the Gaussian mixture. So what's nk? What says there, all right. I know, that's why you don't want to tell me, because you are reading from a distance and I cannot see a damn thing from a short distance, okay? All right, so nk is the effective number of data points associated with component k. So, and what's xk? What is this whole thing? It is the centroid of cluster k, where every point is weighted with the responsibilities, right? So you notice, what I could have done is I'd say, take the points that belong to the cluster k and take the sample mean of those points. But every point belongs to every cluster, and to what proportion it belongs is defined by gamma. So I have to take the sum over all points, which is convenient, right? So you don't really have to say over the points in cluster k. No, take over the points, weight them with gamma and k, and you're in business. And when you take the joint log likelihood, the expected value of the joint log likelihood, and we take derivatives with respect to the centroids, these mu's, the answer comes for the vector mu k, that it is actually, as you anticipate, right, is it's literally the sample mean of the points that belong to the effective points that belong to that cluster K, right? So this xk bar is what you get out of this. So you may say, then I didn't really need to do the algebra. Well, but you need to do the algebra to understand that there is no magic, and somehow this EM algorithm and this expected joint log likelihood, it actually gives you an answer that is a common sense answer. And pi k, right, the mixed coefficients come to be literally the proportion of points that belong to cluster K, exactly as you expect. There is a pathology, by the way. I don't know if this is you have any problem in your homework. There is a pathology here, and the pathology is the following. If somehow you do the mistake and you initialize the centers, because you remember to start the EM algorithm, you have to say how many clusters you want, what's capital K, and in this case also what is the center of each cluster. So if you start and you put all the clusters at the same value, guess what happens? At every iteration of the EM algorithm, it will keep telling you that the centers of the clusters remain always the same and equal to this value x bar, which is the sample mean of all the points. Right? And the derivation is given of these little two equations. So if again, you start with something like this, all right, you will always be trapped to the centers having all the same value. You will never be able to generate the right solution. And so when, if you look this in either, in Murphy's book or in the statistical toolbox in MATLAB, you will see the initialization for these Bernoulli distributions of the centers. It's always done in a random fashion in a certain, in some interval. Okay, so you never select those to be the same. The reason you see it here. All right, so so let's see. Just to finish this, an example again. We take the digits 2, 3, and 4. We take 600 of these digits. They are binarized, so basically they're black or white. And we use 3 Bernoulli distributions. We do 10 iterations. We initialize the pi k's to be 1/3. We put randomly the centers as we discussed. And of course, you normalize them to satisfy this. And this is what you get, all right? So these are the training data. And these are the centers of the 3 clusters that you identify. No bad, right? You provide handwritten data, and it tells you there are 3 clusters, and they are centered around 2, 4, and 3. These are the means of each component, right, in the mixture. If you only use if you only use one component in the mixture, basically you get sort of an average center that looks, it's a little bit blurry because it's an averaging, if you like, it's a pool average of the previous calculation, so it looks like that. All right. You can generalize this actually, instead of having Bernoulli distribution, you can make it really fancy, right? So we had a d-dimensional vector, and each component of the vector was a binary component. Now you can say each dimension, it's a k-dimensional variable, and only one of those k variables it's on, and you define being on or off with probability mu k. The calculation for that is sort of a trivial expansion of the slides that you have seen, so not a very complicated problem to do. All right, so let's look at the map estimation on these problems. So I'm going to do the map estimation for the Bernoulli case. All right, so help me to understand. So this is the expected joint log likelihood, where actually I have now introduced the prior distribution in the parameters. So not only I maximize the likelihood, right? I maximize the unnormalized posterior, if you like, right? Remember, the joint log likelihood times the prior gives you the anormalized posterior of theta. So this is the anormalized posterior. So tell me every term. From where do they come? The two terms that I see inside the brackets, what are they? The two terms inside the brackets, from where do they come? Or give me a name of them. Have we seen them before? Give me an English name for the bracket. I don't hear a thing. Before we had seen gamma times the log plus this log, right? So what is that with words? With words. No, better than that. It's the expected complete data log likelihood. I mean, every single word is not like comes out of nowhere, right? It's expected because I use gamma. It's complete data because this is the likelihood of x and z, and it is a log likelihood. All right? It's called expected complete data log likelihood. And what is this term? Log of pi, that it depends only on the mixing coefficients pi. So means what? That I have put a prior on what? You put a prior on pi, and can you actually tell me what prior? Okay, I can see it says there. What prior you will put on a mixing coefficients? Because maybe you already have seen it in earlier lectures. Huh? I heard something I didn't like, or I didn't hear it well. What was it? What did I hear? I heard something. The what? For pi, no better. All right. It's actually sort of a generalization of beta because now we have many components, right? Beta has only two terms. So what is a generalization of beta? I can see here it screams on me. A Dirichlet prior. All right? For the mixing coefficients, we'll put the Dirichlet prior. And you remember I told you, right? If you wanted to do an infinite mixture of components, of Gaussian components, you use the Dirichlet process, right? Which is a very modern generalization of these mixtures. And I wish one of you would pick up a project like that because it's very relevant to everything. But everybody picks up projects that they're sort of resonate things you know from high school. So this is a Dirichlet. And what is that? So we have, k components, right? And each component, say for the Gaussian mixture of was the mean and the covariance that they were unknowns. So that's the parameters theta k, or in the case of the Bernoullis, they were the centers of each of the mixtures. So this is the log prior of the parameters of the conditional distributions, all right? And obviously, what will you? So, for example, in the Bernoulli distribution, what will you use as a prior for the centers mu? Remember that when we wrote the Bernoulli distribution, it was mu to x, 1 minus mu to 1 minus x. So what's the conjugate prior to that? Binomial? Binomial is okay, but there is a count there, and we don't have any count here. So it's really a beta distribution. Okay? So we're going to use a beta distribution. If this were Gaussians and the mean and the covariance were unknowns, what will be this distribution on the parameters, on the mean and the covariance? What's the name of that nice distribution we had seen that was looking a little bit complicated? So what's the nice distribution for the mean and the covariance? a multivariate, in a multivariate setting. How do we call it? Normal, continue. Inverse wizard, right? Normal inverse wizard. Okay? I mean, if it was in 1D, it would be normal inverse gamma distribution. Okay? All right. So if, let's say this is how it looks for Bernoulli distributions. So if you take the expected joint data log likelihood plus the log of the prior, this is what we had before. Now this comes from the Dirichlet, right? This whole thing comes from the Dirichlet prior on the mixing coefficients. This comes from this beta distribution for the means, okay? And there's a mistake somewhere there. No, I'm sorry, what am I talking about? So what did I say this is? You never correct me if I say something wrong. So what is that? Because I see here I prime from 1 to D. So you remember the parameters were the centers for each cluster, right? And what's the conjugate distribution for the centers? What distribution, what log of what distribution is here? You remember the beta distribution is theta to the power alpha minus 1 minus theta to 1 minus b. So this is the log of what distribution? Beta. And this is the log for the mixing coefficients pi, and that's the log of the Dirichlet distribution. All right? All right. So the rest is really doing gradient calculation by hand. So if you take derivatives with respect to pi, derivatives with respect to mu k, you get these two nice results. And always remember, when you take derivatives with respect to the mixing coefficients, you really have to put a Lagrange multiplier to enforce that the sum is equal to 1. Okay? So you cannot do the optimization otherwise. So you basically get results that are very familiar with things we have seen in an earlier Bayesian lecture. So instead of having pi k being nk over n, now it's nk plus alpha k minus 1 divided by n plus alpha 0 minus k. And remind me, what is alpha 0 for the Dirichlet distribution? What is alpha 0? It's a shorthand notation of what? Of the sum of alpha k's. Okay? Of the sum of alpha k's. And similarly, for the centers mu, you get this very nice closed form result, right? Very nice, very appealing, basically. All right, so if your mixture is a Gaussian, I give you the results for that as well. So you are going to use a prior that is an inverse, normal inverse wizard distribution with parameters mu0, k0, nu0 as 0, right? You remember a normal inverse wizard means the conditional sigma, the distribution of mu is a Gaussian, right? And then you have a wizard, an inverse wizard distribution for sigma, right? So you can think of this mu given sigma, then times the distribution of sigma. And so if you do the algebra, all right, it comes out, and that's why you need to know everything about the multivariate Gaussian. You remember all the results, right, look like for Gaussians, for the Gaussian mixture, they look like working with each component independently and doing MLE. The only difference for each component, we only use the points that are effectively belonging to that cluster. So you don't really need to do the algebra if you trust yourself. You say, I'm going to use the results for MLE for this normal inverse wizard MLE problem, and I'm going to modify them by throwing a gamma there in the definition of the effective number of points on its cluster, the center of its cluster, and the definition of S. So this formula that you see here, it's basically identical to the formula that you get when you do map estimation for the normal inverse wizard distribution, and for a Gaussian basically with prior that is normal inverse wizard, okay? This is the exact result for the map estimate. This is the exact result for the mean. The only thing that changes is the standard definition having everything weighted with gamma. So literally, I did not do the derivation. I wrote the formulas down, and then I went to check on Wikipedia, and it says, oh, yeah, it's correct. All right? So you trust, and you verify for me. So let me, there's a very nice example in Murphy's book, all right, that demonstrates why you need to do map estimation for this type of mixtures. And let me see rapidly what the setting here is. We are going to do MLE estimation for in high dimensions. Does it say what data points we have? So we have a Gaussian mixture, all right? And on the top, it basically shows the fraction of times that the expectation maximization algorithm fails, all right? And fails has to do with the calculation of the covariances of each mixture component sigma k. So if you try to do this casually, you will see that sigma k comes to be singular, right? It comes to be singular. So if you apply the EM algorithm, right, as you increase the dimensionality, notice that when you calculate the MLE, all right, for the Gaussian mixture, the number of times that the algorithm will fail versus dimensionality becomes really 100% after dimension 50. So the algorithm basically never works. When you do the map estimation, it does fail a few times, depending how you initialize things, all right? But more or less for high dimensionality, you can see here on this plot, the number of failures is equal to 0, okay? So for this implementation, the prior for this normal inverse wizard has been initialized, and the discussion is here what coefficients you use, but more or less the message here is there is a point to actually do a map estimation for Gaussian mixture models because MLE doesn't seem to be stable. All right, so let me, I'm going to finish today with to convince you that this methodology is very powerful and you should use it, all right, without expecting somebody to tell you, oh, you know what, use the EM algorithm. The EM algorithm is everywhere there are hidden variables. So let's do one example. Let's remember the most trivial case of regression models that we did following the notation from Bishop's book. Remind me of the equations. Come on. What's the equation on the top? Give me all the symbols. This is what says likelihood. So what is the regression curve looks like? For every x, what's the conditional expectation of the response? What's my regression line here? Around here. Is it what? You remember at every x, right? And the little x is here, right? I mean, this is so the input is this matrix x of all input points, right? And these are the corresponding responses, this vector. So I write this for each point, the product over all the points. So this is the likelihood for point xn. So what's the regression curve here? What's the equation basically for my regression model? Remind me. You think I can hear? The older you get, the less you want to hear. It's not that the less you hear, the less you want to hear. All right? So you have to say louder. So what's the regression line? W transpose what? X. W transpose phi of x. Where phi of x are some polynomials or some Gaussian kernels or whatever. Okay? And beta is a noise parameter. All right? It's a precision, the noise we get in the likelihood. The second thing is we put a prior on all the parameters, and this trivial model, the precision for in the prior model was always the same for all w, so we put a precision alpha, and the marginal likelihood basically, all right, involved integration of w, right? So this is basically the denominator in the Bayes rule where we compute the posterior of W. So this is the likelihood times the posterior with W integrated out, and we computed and we gave expressions for this marginal likelihood in terms of alpha and beta, and we use this marginal likelihood to do what? To apply what algorithm to compute alpha and beta? What was the name of the algorithm? Very important to compute the hyperparameters alpha and beta. Empirical Bayes, yes, in a more general sense. So this was the evidence approximation also, right? But more or less the same thing, okay? So the evidence approximation, we did the optimization, we took derivatives with respect to alpha and beta, and I'm going to show you those equations we got that they were sort of interconnected, okay? But we had a framework to actually optimize the hyperparameters alpha and beta. So I don't want to show you any equations, and without looking at the slides, tell me, why is this problem related to EM? I mean, give me some thoughts. Why is this relevant to expectation maximization? I don't, what hidden variables? What does that mean?
The hyperparameters to estimate your hyperparameters.
To estimate the hyperparameters continue?
You need to use EM because they're not really known.
What is not known?
Hyperparameters.
I know the hyperparameters are not known, all right? So we should take those to be the latent variables, all right? I haven't thought about that. I don't think it will work, all right? So don't read the text here, all right? I want you to look at this equation there, the third equation, all right? And tell me what are the hidden variables here? That somehow, if I knew them, my algebra would be very easy, certainly to calculate evidence, all right? But somehow, so if I knew them, the algebra would be very easy. I don't know them. So what parameters are those? The W's. All right? So here you notice, so W, and I always tell you, right, when you do regression, W is the means to facilitate the regression model. You don't really care about W, because at the end of the day, even, you don't see the predicted distribution here. There's no W, right? We don't care about W. So we are going to treat it as a hidden variable, all right? And so if we knew W, maybe the algebra would look simple. Since we don't know W, we can do some expectation maximization iterations, where in the expectation, we're going to compute the posterior of W. And the posterior of W, by the way, we have an analytical expression for it. And in the M step, we're going to optimize with respect to what parameters? Beyond W, what is the other parameters that are not known that we would like to optimize by maximizing the evidence? Alpha and beta. It's as simple as that. All right? So the idea is, again, let's compute the posterior of W and then do an EM, recomputing the estimates of alpha and beta. The question, of course, is, if you do that, do you actually get the same results as the evidence approximation and the estimates of alpha and beta? And what do you think? Are the results, is this so powerful that somehow the results will come to be the same? Because remember, right, we do, in the evidence approximation, we do the integration exactly because we plug in everything correctly analytically and we integrate exactly, and then we maximize with respect to alpha and beta. In the EM algorithm, we're actually, we compute the posterior and then the joint log likelihood, and we start iterating because the posterior depends on alpha and beta that we don't know, so we have to do iterations. So are the two methods going to give the same results? And the answer is most probably not, but when the two methods converge, because they have the same objective, you better get the same answers. But not in the iterations in between. So the updates will not look the same. So I want to do this, right? And maybe on Thursday I'm going to do a more complicated example, because this is very, very powerful idea that comes in regression models, in for unsupervised learning. It comes everywhere. So I remind you what the posterior looks like. So given the data t, right? Given the data t, we compute the posterior of w, and the mean is given like this, where the inverse of Sn is given like that. And you remember phi is my design matrix that contains the values of the basis functions evaluated at each of the training data points. Okay, and I put the prior here. All right, the precision is basically alpha minus 1i. Okay, so we need to compute now, to do an EM algorithm, right? We need to compute the joint log likelihood, which is weird here, right? Joint log likelihood. So it's the joint likelihood of t and w, all right? And can we do this? Of course, because the joint distribution is the likelihood of t if I knew w, which we know it's a Gaussian. It was the first equation on the previous slide, plus the distribution of w, which is our prior that looks like that. All right, so this, again, this thing here is directly given by this equation, right? That's my likelihood model. And then I have plus the prior, and the prior is this. So I can write this exactly. And then now I'm ready, when I put this joint log likelihood together, I am ready to take expectations with respect to what now? So I have the joint log likelihood, and we're going to take expectations with respect to what? Before, when we did the general framework, the expectations were with respect to what variable? The what? W. Before we had z, right? So now would be the posterior of w. So everywhere you see w, you need to put expectation. That's the posterior expectation. And remember, the posterior of w is given analytically by this nice formula, right? That's the posterior of w given by this nice formula. So if this is a Gaussian, I am sure you can compute the posterior of w transpose w, right? So I give you the formulas here, okay? All right. So this is the expectation of w transpose w using the results for the posterior, and this is the expectation of Tn minus w transpose Vn. If these formulas look to you cryptic, expand every term and substitute, the mean and the covariance of the posterior, and you will see that these results are correct. So you plug in this term, you plug in that term, and then in the M step in the EM algorithm, we have to take derivatives with respect to alpha and beta, right? We have to optimize the expected joint data log likelihood, okay? So basically, again, this equation, we have to take derivatives with respect to alpha and beta, and the results come to be direct, all right? This is alpha inverse, this is beta inverse, and I am going to put a thing on the next slide. These are the results with the EM algorithm. These are the results that we got with the evidence approximation. You remember what was lambda in the evidence approximation? I mean, not precisely, but at least, with what was related. What was lambda in the evidence approximation? It was the eigenvalues of some version of phi transpose phi or x transpose x of the input design matrix, okay? Scaled with some parameter, okay? But certainly this required solving an eigenvalue problem, which computationally is as expensive as doing a matrix inversion, okay? So, notice the computation on the EM algorithm is as expensive because it requires that you know the matrix Sn, but really the only matrix that we know is Sn inverse. So the computational cost of either doing the evidence approximation the standard way or doing the EM algorithm seems to be the same. All right. Now the two equations that don't look the same, right? Can you remind me, by the way, what was the physical meaning of gamma when we did regression? Because we discussed about the physical meaning for gamma. It was the effective number of parameters, right? The effective number of parameters in the model, okay? We don't have any interpretation like this in here. So the question is, are these two equations strange? You know, are they consistent? Well, you know, the proof is on this slide, right? That if somehow you have reached self-consistency and you take the equation for gamma and you plug in the value that you get for alpha and you rewrite them, you actually get the same identical equation as with expectation maximization. All right? So basically, these two equations, right, for alpha and gamma, if you plug in alpha inside here, all right, and you solve for alpha, you effectively get exactly this equation. But those two equations become the same when the algorithm is converged, because we solve them iteratively. You remember when we were doing updates in the evidence approximation, we will first compute gamma, then plug in gamma there, get an alpha, then without alpha get another gamma, and then another alpha. So when the self-consistency converges, the two equations, basically we can plug in alpha there, and it comes out that the alpha that we get is the same as the one that's coming from expectation maximization. Now, why should I actually care? And maybe even on this problem, I should do an expectation maximization. The answer is very simple, right? These results are very particular to the regression problem we consider. This type of analysis, by maximizing the joint log likelihood, the expected value of the joint log likelihood, it's very general. You can do it on any problem. I mean, anything that you don't know, you can call it hidden variables with only, the idea here is that you will call something hidden variables if somehow this joint distribution has way more easy form to work with than the conditional distribution of T given W. And in this particular case, right, the form, because this is a Gaussian, this is a Gaussian, you know, you have the sum of two Gaussians, it works very nicely. Otherwise, you know, if you don't get any simplifications, you're not going to bother to do this, okay? So now the, all right, so we said for self-consistency. Now there is another regression model that I will, I do not want to delete those 3 slides from this lecture, so you can come back to it later in the course. But there is a method that goes with the name of relevance vector machine for regression models that allows you to explore sparsity. So it forces some of the coefficients in the regression model to become unimportant. So it selects basically what input dimensions are important to the model. And the way the relevance vector machine does this is by using a prior model where you don't put on all the weights the same prior, right? You put different, so this matrix A that you see here, this precision matrix, is diagonal, but you put sort of a different alpha for each W. And it comes out that when this alpha takes some critical values, like when, let's say, alpha goes to infinity, and it may be actually the opposite, right? But when alpha goes to infinity, the corresponding W disappears from the problem. It doesn't contribute, basically, in the calculation in a simple manner. All right? So the only thing different from before is that the prior doesn't have just an alpha there, but there's a matrix A, which is a diagonal, and you assign a different precision to each of the, the input directions, to each of the vectors W in the model. So you can actually work all the details for this relevance vector machine. The notation follows literally our regression model. So what you need to do is you need to form the expected joint log likelihood, and you see here, if you knew W, right, that's the likelihood times the prior. The only difference now is the prior model will change from before, right, because we're going to use a diagonal matrix A. So if you do the algebra, and I advise you to do it because this type of calculations appear in variational methods everywhere. You expand everything, and then what do you do at the end? You take expectations with respect to the posterior of W. And that's what I have done, right? So there is a W there. There is W transpose there. So when you take expectations and use the exact posterior of W, exactly the same equation as before, you actually have the expected value of the joint likelihood looking like this, and you can do the optimization, and the results basically come in closed form solution that you see on the slide. And before the light turns off on me, I'm going to say, see you on Thursday.